Alright, in 6.2 here, what we're going to talk about is more vector stuff, and this really all revolves around the dot product of vectors. So, what is the dot product? Well, the dot product of a vector, and you need two of them, and really all you're going to do is you're going to take this first number from your first vector times the first number on your second vector, and then you're going to take the second number on your first vector and the second number on your second vector, multiply and add. So it looks like this right here. It's really an easy thing. In fact, if we look over here on the right under find each dot product, it's really simple. It's just going to be 3 times 5 plus 4 times 2. And whatever that turns out to be, that's what your dot product is. And so for this guy, this would be 15 plus 8, which is 23. On the next guy, you're going to have 1 times negative 4 plus negative 2 times 3. And so this is going to be negative 4 plus negative 6, which is negative 10. So these are not hard things to do. If you've got one with the standard form here, standard unit vector form, you're still just taking the first number times the second number, and then that second number, which in this case is a 1, okay, because there's just one j there, times the 5. So you're going to end up with 2 times 3 plus negative 1 times negative 5. And that's going to be 6 plus 5, which is 11. And that's how the dot product works. It really is that easy. And then over here we've got the properties of the dot product and how it works. So you can do all of these things, and I would encourage you to have these easily accessible in your notes, and just be familiar with them. They're not hard, but they're just the things that you can do with the dot product. Okay. And so if you need to pause the video or whatever and get these written down, do that. But again, these are just some of the things that you're going to need. Okay, on this one, what we're going to do is we're just going to use the dot product to find the length of a vector. Well, remember that the length of a vector, the length of a vector is going to be the magnitude of u, which is the square root of the stop minus the start squared. So it'd be the square root of u1 squared plus u2 squared. So if you're asked to find the dot product, what's going to happen is these u1s and u2 squareds are just going to become basically those same things, and so we would just dot u with u, and so what you're going to end up with is 4 times 4 plus negative 3 times negative 3. Well, guess what? Both of those, that's the same exact thing as the magnitude. So again, it's just using the dot product. It's just another way to work this problem out, and so you're going to end up with the square root of 16 plus 9, which is the square root of 25, which is 5. And that's all there is to it. So don't let this guy be hard at all. You can also use the dot product to find the angle between two vectors that are non-zero vectors. That's got to be non-zero. And remember, if you do that you're going to be working with an angle theta, and that theta has to be between 0 and pi. It cannot be any larger than that. Once it goes past pi, then you're looking at a different angle that has to be in between. So if we're going to do that, if we can find the dot product or know an angle, then we can use this top equation here. Again, we'll need, we can only be missing one piece of that information. So if we can find the dot product or magnitudes, we can figure out what the theta is. On the other hand, if we know the theta and we know most of this angles here, most of the vector information here, we can find what's missing. But these two guys are related. One's just the inverse of the other, so that we can find the exact specific degree that we need to have to find theta. And it's just using trig on your calculator. So either, whatever mode you have your calculator in, make sure that you're consistent throughout the whole thing. Okay, and so probably on this, the other thing I should say is if 0 is less than pi, then theta will also be less than or equal to 180. And for our purposes, it might just be easier to work in degree mode. So anyway, so let's give it a whirl. Let's try down here where I've got the cosine of u and v. Find the angle between the vectors. That's going to be this angle theta right here. Okay, and so what I'm going to do is I'm going to take u dot v. So the theta is equal to the arc cosine of u dot v. So I'm going to have 2 times negative 2 plus 3 times 5. Whoops, not comma 5, but 3 times 5. Let's do this. Over the magnitude of u times the magnitude of v. Well, remember on the previous example that you can use the dot product to find magnitude. So in this case, it's going to be 4 plus 9, which is going to be the square root of 13. And then this guy right here is going to be 4 plus 25, which is going to be the square root of 29. And what I would do is I would just punch all of that into your calculator and get an answer. So if you want, go ahead and pause the clip right now and see if you can get the right answer that I get. So I get for theta, and again, I'm going to work in degree mode because I can visually see where the degrees are a little bit easier than I can the radians, and I'm going to get an idea of an angle here, and it's going to be 55.5 degrees. Okay? So that's the first guy. Looking over here at the second guy, it's going to be the same kind of thing. But now, notice that if you go the normal way, the angle that we would look for, we've been trained, is to look here. But with vectors, that's not going to work. You have to find an angle between 0 and 180. So what that means is I'm going to find this angle right here. Okay? And so what have I got? Well, I've got theta is equal to the arc cosine of the dot product, which is 2 times negative 1 plus 1 times negative 3, divided by the magnitude of these guys. So this is going to be 4 plus 1, which is the square root of 5. This is going to be 1 plus 9, which is going to be the square root of 10. And again, if we want to stick in degree mode because it's something that we're going to recognize a little bit easier. So if you want to take a time right now, again, pause the video and see if you're going to get what I get. And when I do my math and punch it in, I get 135 degrees. And that's all there is to it. So it's really a pretty cool deal the way it works out. Now, if you get a dot product of, if you do this with 0, and you get a 0 in there, you're going to have a 90-degree angle. So that's also interesting. Keep that in mind as well. Okay, so orthogonal vectors. This is a word that you don't use every day, but orthogonal vectors are two vectors who have a dot product of 0. And if two vectors have a dot product of 0, that means that those two vectors are perpendicular. So if I've got a vector that goes this way and a vector that goes this way, when I take the dot product of those two guys, I'm going to get 0, because this angle theta right here is going to be equal to 90 degrees. Or it could be pi over 2, depending on if we're working in radians or not. This is a really easy thing. The only thing that's going to be difficult on this part is the terminology, but orthogonal is unique enough that you should be able to remember it fairly easily. But just take the dot product of these two guys. 2 times negative 6 plus 3 times 4. And when you do that, you get negative 12 plus 12, which is 0. So are these two vectors orthogonal? Yes, they are. And if you graph them and you draw them out on an xy axis, so let's just do that real quick. So here's an xy axis. So if I draw the vector 2, 3, I'm going to go 2 this way, 3 this way. And if I draw the vector negative 6, 4, then I'm going to go negative 6 this way, and 4 this way, and looky there, they're going to be perpendicular. So it's really kind of cool the way it works out. Okay, vector projection. This is a little bit more of a complicated kind of thing, but it is really interesting how it all works. But basically what you're going to have is a vector projection of u, vector u, which is this green guy, and we'll call it PQ, onto a non-zero vector. Again, you have to have a vector of some length. And we're going to call that vector PS, which is that whole thing, the red and the blue together, is the vector PR, and is determined by dropping a perpendicular line from Q to the line PS. And what we're going to do is we're going to split the vector U into two parts, PR and RQ. So what they're saying is that we're going to have two parts to this vector. U is going to be made up of this guy, let's see here, right here, and this will be like U1. And then it's going to also include this part right here, which would be U2. So if I take the PR plus RQ, I should get U. Okay, if I take PR, this distance right here, and RQ, this distance right here, and add them together, notice when they add up, they make the one vector U. So what we're trying to do is find those two things, and we use a formula for that, and the formula is this guy. It looks really weird, but it's not that bad. It's just going to be u dot v divided by the magnitude of u squared times the vector v, because remember with vectors you get a direction off of this guy, so this guy's going to be the direction of the projection. Okay, he's going to be the direction of the projection. And this guy right here, this part is going to end up being the magnitude of the projection. So we're going to have a magnitude and a direction. That's our vector. And so it's really kind of interesting the way all this stuff works out. So let's try an example. Find the projection of u onto v. Then write u as the sum of two orthogonal vectors. One of them will be the projection of u onto v. Okay, so let's do this. Let's go ahead and take our formula, and if you need to rewind it real quick and get it or whatever, but I'll just write it again. So we're going to have the projection. If we take the projection of u onto v, that's going to be equal to the dot product u dot v over the magnitude of v squared times v. So one of the things that I've got to do right off the bat is find the dot product. Well, if I do u dot v, this is going to be 6 times 5 plus 2 times negative 5, which is 30 minus 10, which is 20. Okay? And, excuse me, then I want to find my magnitude of v and square it. So remember, if I find my magnitude of v, that's the same thing as the square root of 5 squared plus negative 5 squared. That is a really weird looking 5. And so if this is what my vector magnitude is, then when I square that, I lose the square root. So this is going to be 5 squared plus negative 5 squared, which is 50. So here's the two pieces that I need, and then I need this vector right here. Okay, so this is going to give me my direction and my magnitude. Well, what's my direction? My direction is going to be 20 divided by, I'm sorry, my magnitude is going to be 20 divided by 50, and the direction is going to be 5, negative 5. So what we're finding then, and I'll change this real quick, we're finding the blue vector. Okay, we're finding the blue vector, that U1 vector. And so that guy is going to end up being exactly, and I'll continue it in blue here, is going to be 100 divided by 50, and negative 100 divided by 50, which is the same thing as 2, negative 2. Okay, so there's my vector projection. All right, and that's this guy right here. This guy right here is the vector 2, negative 2. Well, what's this writing U as a sum of two orthogonal vectors? Well, I need to write, I need to figure out what U is, but based on the fact that I need this vector to add. And I don't know what that is, but I can find it because I know that my vector U, which is in green, my vector U is 6, 2. And what we want our equation to look like is this. We want this vector 2, negative 2 plus, let's just call it, let's see, we got U and V. I'll just call it Q, for lack of a better word, Q1 and Q2. So, in other words, for my U2 part, okay, this is my U2, this is my rock band, 2 plus what is 6? And in this case, 2 plus 4 is 6. Negative 2 plus what is positive 2? And the answer to that is 4. So the last part of this is the sum of two orthogonal vectors. Then I've got them. Okay? And they're going to be U. Okay? The vector U is equal to the vector 2, negative 2 plus 4, 4. So it looks horrible and painful, but it is not that that bad. But the projections are really interesting. You can do some really cool things with those. Okay, some other things that you can do with vectors is you can use them to find a force, like Star Wars. Use the force, and basically what you're going to have is you're going to have some weighted object, which is this like brownish-looking box here. This guy right here. Okay, he's going to be weighted down. How much he weighs, we don't know. We will know, but for this particular guy, it doesn't matter. And then I'm going to have like some force pulling my box, and it's this blue guy. Okay, and I'm going to pull it though so that the box slides across my surface, and that's going to be the V guy. And so we can use a vector projection to determine exactly what I need to do to move that box or object or whatever. So if we pull a box with a force U, the effective force in the direction of V is the projection of the vector U onto V. So the vector projection can help us figure out forces. Well, what does that look like? Well, I know it didn't really snow for us over the break, but let's say Rowan is on a sled on the side of a hill inclined at 45 degrees, and the combined weight of Rowan and the sled is 140 pounds. What force is required for Marin to keep the sled from sliding down the hill? Yes, I know it should be the other way around, but Marin's scheming. Okay, so she's got a plan. Well, we just need to figure out what Marin needs to do to let go, to keep the sled from sliding down the hill, because her whole goal is to not do quite that much. She can just barely let it go. So what do we need to do? Well, we've got to find out these different vectors. Okay, so let's say that gravity is working here. Okay, gravity is working, and since gravity works, Rowan is going to be pulled by gravity, and it's going to be this guy right here. Okay, and he's going to be this force being pulled straight down. And if we look at that, we would say that this would be 0 and negative 140. Okay. The other way that you could look at that would be negative 140j if we look at the standard unit vector form. Okay. And so there's that guy. Well, the hill then also is going to be a vector, and that hill has an angle of 45 degrees. And, you know, the hill's really long, but we just basically need a vector in that direction. So what we could do is we're just going to look at a unit vector so that we've got a direction, and we're just going to take 1, which would be a magnitude in this case, again, just for direction purposes, times the cosine of 45 degrees, and then 1 times the sine of 45 degrees. This is the direction that Rowan is going to slide once Marin lets go. So this is going to be square root of 2 over 2 and square root of 2 over 2. And again, there's two different ways that this could be written. It could also be in this like standard vector form here, which would be square root of 2 over 2i plus square root of 2 over 2j. Okay, this is how it could look. So what we want is we just want the projection. We want the projection then of these two vectors. So how does this shape up mathematically? Well, we're going to take the force 1, this 140, and the force 1 is actually, it's right here, right there. That's what Marin needs to use to hold on. So here's how it's going to go. We're going to look at the projection of the big force times the vector divided by the direction squared. Okay, and so here's my force vector here, here's my hill vector here, my direction. Okay, and so let's see, and we're going to multiply that times the vector v, so we get a magnitude and a direction. So big force dot product here. So notice that this is 0 times square root of 2 over 2. That's 0, kids. And so then we're going to do negative 140 times the square root of 2 over 2 divided by the magnitude of this guy right here. So remember, that's going to be 2 over 4 plus 2 over 4, which is 1. Okay? So that works out real nice. So basically what you end up with is negative 70 square roots of 2. Whoops, not, yeah, negative 70 square roots of 2 times that vector v. And that's pretty much all there is to it. It's not that bad of a guy. So what force then is required to keep Rowan from sliding down the hill? Well, the biggest part of that is right there in front. So I've got a magnitude with direction. And remember, the magnitude is how much force needs to be used. And so here is the part that I'm really interested in. And so for Marin to keep rowing from sliding down the hill, that force sub 1's got to be negative 70 square roots of 2. So that's all there is to it. Alright, the last thing that you can do is you can look at work. And so if F is a constant force whose direction is the same as the direction of AB, then the work done by the force in moving an object from A to B is this guy right here. And remember, this is magnitude and magnitude. Okay. And so a force is a constant force in any direction. The work done by the force moving the object from A to B is the force dotted with the direction, okay, which is the same thing as the magnitude of the force times the magnitude of the direction times the angle. So between them, so where theta is the angle between. Except for the sign, the work is the magnitude of the effective force in the direction of AB times AB. So it looks really weird, but the process is not that bad. So let's just look at an example. So find the work done by a 10-pound force acting, that should be in the direction of 1, 2 and moving an object 3 feet from 0, 0 to 3, 0. Okay. So basically what we're going to do is we're just going to take F and this should be dot, by the way. We're going to take F and dot it with the direction that we're going. Alright, so here's the direction that we're going, and my force is 10, and it's being pulled from 0, 0 to 3, 0. Okay, so here's what you're going to do. We're going to take 10 and multiply it with this guy. So I'm going to take 10 times the vector 1, 2, and that's going to get me the vector 10, 20. But I need this to be a unit vector, so I'm going to also divide by the magnitude of this guy. Okay, and so the magnitude of that guy is going to be this would be 1 plus 4, so it would be the square root of 5. So here's a unit vector in the direction that I'm going, and it's going to look like, 10 over the square root of 5 and 20 over the square root of 5. Okay, so there's the force that is being applied to the object. Then what we want to do is we want to put this in the direction of 3, 0. And so we're just going to dot this force with my other vector. Well, what's my other vector? Well, if this is my force vector, 1 unit of force, then my direction vector, the AB one, for lack of a better term, is just this guy, 3, 0. And so all you're going to do is use the dot product, and you're going to take 3, 0. Let's see here. You're going to take 3 times 10 over the square root of 5 plus 0 times 20 over the square root of 5. And this will equal your work. So it looks like a horrible thing. It's not that bad, which for this particular problem is 30 over the square root of 5. Now with work, let's go ahead and decimal this out just a little bit. So this would be 13.42, and 13.42 watts. Well, we've got pounds, and we're moving in feet. So this would be in foot-pounds. Okay, and that's all there is to it.